It's been a few weeks, and thanks to tests by a few Chinese scientists, we can probably say that LK-99 isn't a room temperature superconductor. The hype has largely died down. LK-99 has vanished off people's social feeds and science news. I suppose we can keep on waiting, but right now, it's so over. Oh well, it wouldn't have done anything for the semiconductor industry anyway. I did some follow-up work since the last video, and even if we hit the jackpot tomorrow and find a true blue room temperature superconductor, it'll be nice, but hardly a revolution. In this video, some irresponsible thoughts about superconductors and semiconductors. The first thing I thought about when I thought about superconductors for chips were interconnects. In an integrated circuit, interconnects are wires for transmitting the electrical signals between the transistors and other circuit elements. These interconnects are usually, but not always, made from low-resistance metal, so we call them metal layers. The wires are surrounded by dielectric material, intermetal dielectric layers, that serve as insulators. For a long time, we used trusty silicon dioxide for this. These layers sit all jumbled about on top of the silicon transistors, like how stratum look like in geology. Generally speaking, an IC has two types of interconnects, local and global. Local interconnects occupy the chip's lowest levels and connect local circuit blocks. The wires are very short, so designers are less concerned about line resistance than they are about other factors like heat. So I don't think a room temperature superconductor, which would be quite sensitive to heat, makes sense here at all. Global interconnects are higher up in the stratum. They connect distant parts of the chip, delivering important signals like synchronizing clock signals or power to run the transistors. For this reason, they have great size, they look thick, solid, tight. The distance they have to span also means that they must be made from low-resistance metals like aluminum or copper. I was very curious about this. In today's most advanced AI accelerators like the NVIDIA H100s we use for massive models like ChatGPT, some 80 to 90% of the power budget is spent on simply transferring data around rather than actual computation. Will superconducting interconnects simply wipe that out? So I asked MIT PhD Alex Sleds for a few thoughts. He's a photonics researcher with a background in semiconductor devices and interconnects, and of course he's a good friend of the channel. I did a video about his work in neural networks and photonics a while ago. Alex said, at short lengths of wire, having a superconducting wire will help significantly decrease the energy consumption to transmit a 0 or a 1. When he mentions short, he means as in the context of wires on the chip or between multiple chips like in a chiplet scenario. He then adds, however, this energy will not become free, since wires will still have a capacitance and an inductance that stores in the electrical/magnetic field of the current flowing through the superconductor. What I think Alex is saying, if I get it wrong, it's because I'm too dumb to understand his words, is that even if the interconnects suddenly possess superconducting powers, its electric current will still interact with its surrounding environment in a way to cause it to leak power. When you push a current through a wire, that wire creates an electric field around itself. Some of the current's energy gets stored in that electric field, causing loss. This is capacitance. The wire will also produce a magnetic field, and that magnetic field will store some of the current's energy too. This is inductance. So, in terms of energy consumption, there's going to be some improvement. That will especially be the case for global interconnects for transmitting power rather than communication signals. But the power consumption gains might not be as dramatic as I might have initially thought. What about computing speed? A substantial portion of the computer's cycle time is spent waiting for data to arrive. So, if the interconnects can carry the data around faster, then that's great. But there are fundamental limits on how fast we can make this. The absolute ceiling in signal speed, the fastest that anything can possibly travel through any medium, is the speed of light. And unfortunately, signals cannot travel at light's full speed because the wire is not a vacuum. Additionally, we need to consider a form of interconnect delay, known as resistance capacitance delay or RC delay. Like as I mentioned earlier, the interconnects store charge. These delay the electric signal's transmission to the receiver. Capacitance depends on the dielectric material surrounding the wire. That material has a dielectric constant called K value. It has little to do with superconductors. So even if we cut the line resistance to zero, we still have to deal with the capacitance part of the delay equation. I wonder if the speed gains will be as significant as I initially thought. There's one last thing about the interconnecting that I want to mention. Remember in the first superconducting video when Kamerlingh Onnes, the discoverer of superconductivity, tried testing superconducting lead wire to generate electricity? He discovered that superconductivity requires not only a low enough temperature, but also a low enough magnetic field and a low enough current density. After the discovery of high-temperature cuprate superconductors, people investigated using them for interconnects and superconducting integrated circuits. Such superconducting interconnects, when matched with the right circuits, can indeed get very fast. The concern, however, is the current density, which is defined as the electric current divided by the superconductor's cross-sectional area. As it turns out, the cuprate's critical current density limits are not very high. So in order to run integrated circuit operations and stay under those limits, the interconnects have to be very wide, perhaps even a centimeter wide, which for most digital circuits is unfeasible. This is why the cuprates never made headway into the integrated circuit arena. LK-99 or any room temperature superconductor may suffer the same issues. If so, then it is just a scientific curiosity, and copper retains its dominance. Even if the new superconductor somehow miraculously fits into the current IC box, quote-unquote, we have the manufacturability concerns. I asked Dylan Patel, chief analyst at Semi-Analysis, to say a few thoughts. He said, while LK-99 seems to show some promise as either an extremely low resistivity material or in fact even potentially a superconductor, the manufacturability of it is still in question. While it does seem to be a fairly simple process for a low purity, low volume amount, scaling this at high volume at high purity with less than 1 part per billion defect is going to be a tremendous challenge. Dylan has a very good point. TSMC has said that a single integrated circuit can use over 100 kilometers of copper wiring. They produce billions of chips every month. To me, this is the biggest issue. Any room temperature superconductor will be a complex alloy, and those tend not to scale. How can we integrate it into the existing process flow? It took 15 years for IBM to crack the complicated materials engineering issues surrounding copper interconnects. And that's copper. We've been playing around with copper for 10,000 years. Any room temperature superconductor will have been known for far shorter than that. In 1962, the British physicist Brian Josephson, then a grad student just 22 years old at Cambridge, wrote a paper predicting a phenomena that we now call the Josephson effect. The effect occurs when you put two superconductors next to one another with a certain thin insulating barrier in between them. Very thin, like as in just a few atomic layers thick. The Josephson effect produces what is called a supercurrent, where a direct current flows through from one side of the device to the other despite the physical presence of an insulator. The supercurrent flows without resistance and with little energy loss. This is in contrast with traditional transistor gates, which generate heat as they switch. That heat must be dissipated. The Josephson effect is one of the few examples of quantum mechanics, quantum tunneling, that we can observe, so that is pretty cool. Josephson later won a Nobel Prize for this. Man, they just handing out Nobels for superconductors left and right. No, really, they are. Superconductivity research has won 1/10 of all the physics Nobel Prizes awarded since its discovery in 1911. A year after Josephson's thesis came out, P.W. Anderson and J. Rowell of Bell Labs produced an experimental circuit based on this theory, creating the Josephson junction switch. There are a variety of implementations. The most popular uses niobium as the superconductor and aluminum oxide as the insulator, creating a sandwich structure. They can switch on or off in just a few picoseconds, or a trillionth of a second. We take advantage of this by encoding the data into very rapid pulses, allowing processing speeds of 100 gigahertz or higher. I don't think anyone disagrees that these can get very fast, but there are major issues. Josephson junctions require big compromises and suffer shortcomings in certain aspects. Let me go through a few of them. IBM worked on producing Josephson Junction-based computers for 2 decades, eventually closing their efforts in 1983. One of the major reasons why they finally ended the project was that they struggled with producing a proper superconducting memory circuit. Memory is basic and essential to a computer. The largest Josephson-only memory unit ever produced was a 4 kilobit unit produced in 1990 by NEC. The reason the memory issue exists is that it is extremely difficult to produce these junctions in large densities. Similarly, this is why the most successful Josephson-based systems have been analog systems and the like. Analog systems handle real-world signals like power or sound or the like. They have only a few components, so it's easier for superconductor-based integrated circuits to compete with them. Sensors, too. Alex pointed out that we can use superconducting circuits to produce some of the most sensitive photon detectors, superconducting nanowire single photon detectors. Digital systems, on the other hand, are built with millions and billions of consistent transistors. It'll be far harder to produce a competitive superconducting digital system. Something that might make the most sense would be like a semiconductor-superconductor hybrid module, like AMD's chiplets. This is where we combine semiconductor-based memory systems with superconductor-based processing systems. So, even if we get a true blue, real deal room temperature superconductor, and it fits in the IC critical limits box, and it can be manufactured in sufficient purities, and we figured out how to make dense bunches of Josephson junctions with it, and maybe we can do that hybrid semiconductor superconductor module we talked about to overcome the memory problem, it still doesn't mean that we get to throw off the freezing equipment like Prometheus's chains. As a superconductor approaches its upper limit transition temperature, the number of Cooper pairs in the superconductor declines. If you recall, Cooper pairs are central to making superconductivity work. The less Cooper pairs we have, the more unstable the circuits will be in the real world. Rule of thumb per BCS theory is that we want to keep the system's operating temperature at half of its transition temperature. That is why existing superconducting Josephson circuits made from niobium are kept at 4 to 5 Kelvin, despite niobium's transition temperature being 9.3 K. LK-99's claimed transition temperature is around 400 Kelvin, so its practical working temperature would be around 200 Kelvin, or around negative 99.67 degrees Fahrenheit, or negative 73 degrees Celsius, or 360 degrees Rankine, or negative 9.055 degrees Wedgwood, or 179 degrees Leyden. If we want a true blue room temperature superconducting chip without the freezing equipment, we need to find something more like an oven temperature superconductor, with a transition temperature of 600 Kelvin or 620 degrees Fahrenheit. Refrigeration remains the single biggest limiting factor in superconductor-based computers, and systems in general, adding a big energy usage cost on top of the system. The dream that we all have, the tech optimist's fantasy, is that superconductivity at room temperature is now possible once we get the room temperature superconductor. I was heartbroken when I learned that it wasn't so. If LK-99 is the real deal, it will be a historic scientific landmark. It might also do impressive things for the power transmission and energy industries in the real world, though I'm just saying that off the top of my head without having done the research. But superconductors aren't serious candidates for disrupting existing semiconductor technologies. At the risk of being made an idiot later, I am saying that I don't believe that any superconductor-based computer will become commercially competitive at any time in the future. But hey, the hype was a blast for about a week or so. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the newsletter, and I'll see you guys next time.